I've only got a couple of minutes. I have an idea surrounding the Joule 3 blocking oscillator and Tom Bearden's MEG. I think he's got it wrong. He's close, but I think he's wrong. I'll show you why. We'll just draw a quick Joule thief circuit. Positive rail, center tap transformer, couple of turns. Really think about it, one's positive, one's negative, because the two of these coils sort of oscillate either way kind of stuff. You've got a 1K resistor, traditionally 1K, comes down to the base of a small, say a BC 547 or something similar, a high speed, low power NPN transistor kind of stuff. That goes to ground, and you take your power off there. And traditionally, you hang an LED off there. And it's when those are connected together. It's when the field collapses, is when the high voltage is generated on that side of the transistor, and you can drive your load with an LED or something like that. So you would normally have both sets of coils wrapped all the way around your toroidal core. But what if we introduce, at the moment that core has no magnetism whatsoever. You have to supply it with it. So what if we introduce some magnets into the center of it? You can't really see it very well. It just holds it on the board. Those magnets, however strong they might be, now sit between the two inside surfaces of our core. You've got 50% of the flux going around this side, 50% going around that side. I'll grab a small piece of steel. Somebody's upstairs, I better be quick. There's no lost magnetism anywhere. You can see that, tapping around, it's not sticking anywhere. All that force is entirely contained by the core. Now, if we got our Joule thief, our blocking oscillator, and kept those windings to this side, your base current is going to start up. You're going to start to drive a little bit of current. Where you would normally build your electromagnetic force from scratch, you've already got a significant amount of electromagnetism in that core. And all you're doing is you're nudging the existing force side to side to side. So once this starts, it cascades, so it ends up turning this drive coil on to 100%, which might move a percentage of this already existing magnetic force to the other side. And then it reaches the what do you call it? When the magnetic field can no longer go any harder. Saturation. You saturate your core. The reverse cascade then happens. It starts to switch off again, which means you get your high voltage back out again. But all you're really doing with this core is you're not removing all the magnetic force. You're just moving it to the opposite side or then bringing it back again. Does that magnetic field have an inertia? Does it take a while to come back to equilibrium? Because if it does it only require a tiny knock of magnetic force to get that larger pendulum of your magnet's energy moving? So then, do you then take, instead of an LED, what happens if we put a diode there and a large capacitor, quite large, and then have, let's keep it safe for a while, let's put, oh, there it is. So that was 1.5 volts. Let's put a 10K resistor and just see what happens to the voltage of that capacitor. What does that capacitor voltage do with those firings through that diode? Will that capacitor build up, and will it bleed voltage back to the positive supply rail and get rid of that line? Yeah. What happens? Because we've already got magnetism in a keeper lasting for a very long time, and all we're doing is nudging it side to side to side ever so slightly. Who knows?